Here is a paradox. An object circling at a perfectly constant speed is at every instant accelerating hard. Its speed never changes, yet its velocity changes constantly because the direction keeps turning. In this video, we pin down that motion, its period, its frequency, and the inward acceleration that bends the path into a circle. Suppose the object is constrained to move in a circle, and the total tangential force on it is 0. Then by Newton's second law, the tangential acceleration S sub theta is 0. With no tangential acceleration, the magnitude of the velocity, the speed, stays constant. This special case is called uniform circular motion. The acceleration is then purely radial, given by the radial component vector. A vector sub r of t equals minus r omega squared times r hat. Because the radial component is negative, this vector always points inward, toward the center of the circle. So uniform means constant speed, not zero acceleration. The speed v equals r times the magnitude of omega is constant, and the only acceleration left is the inward one that keeps the object on its circular path. Because the speed is constant, the time to complete one full orbit is also constant. We call this time the period, capital T. In one period, the object travels a distance equal to the circumference. Distance equals speed times time, so S equals v times t. That distance is the circumference, 2 pi times r. Setting them equal, 2 pi r equals v times t. Now solve for the period. T equals 2 pi r divided by v. But the speed is v equals r times omega, so substitute. T equals 2 pi r divided by r omega. The radius cancels top and bottom, leaving t equals 2 pi divided by omega. The period depends only on the angular speed. The faster the object sweeps angle, the shorter the time for one trip around. Closely tied to the period is the frequency, lowercase f. The frequency is defined as the reciprocal of the period. F equals 1 divided by t. It counts how many full orbits happen each second. Since the period equals 2 pi over omega, the frequency equals omega divided by 2 pi. The SI unit of frequency is the inverse second, which we name the hertz. 1 hertz is 1 cycle per second. So we now have 3 interchangeable descriptions of how fast the object goes around: the angular speed omega, the period t, and the frequency f. Know any one, and you know the others. Now the centerpiece. The magnitude of the radial or centripetal acceleration can be written in several equivalent forms, and which one you reach for depends on what you know about the orbit. They are all equal because the speed and the angular speed are tied together by v equals r omega. Start from the form we already found. The magnitude of a sub r equals r times omega squared. That is form 2 in terms of radius and angular speed. For form 3, use v equals r omega the other way. Omega equals v over r, so r times omega squared becomes v squared over r. That is the centripetal acceleration in terms of speed and the radius. For form 4, recall omega equals 2 pi f, square it and you get r times omega squared equals 4 pi squared r times f squared in terms of radius and the frequency. For form 5, use omega equals 2 pi over t, the period form. Squaring gives 4 pi squared r divided by t squared. So the magnitude of the centripetal acceleration equals r omega squared equals v squared over r equals 4 pi squared rf squared equals 4 pi squared r over t squared. 4 faces of one quantity. You pick whichever matches the numbers you're handed. Those formulas came from calculus earlier. Let's see where the inward acceleration comes from geometrically. The same chord and arc trick we used for velocity. Picture the orbit at 2 nearby moments. At time t, the velocity is tangent to the circle. A short interval later, the velocity is again tangent, but it has swung through the same small angle, delta theta, that separates the two radii. Both velocity arrows have the same length, the constant speed v, but they point in slightly different directions. Now copy those two velocity arrows and place their tails at one common point. The little vector that bridges their two tips is the change in velocity, delta v. The angle between the two velocity vectors is delta theta, the very same angle swept by the position. That tiny bridging vector is what the acceleration measures. Now read the length of that bridging vector. The two velocity arrows have equal length v and a small angle delta theta between them, exactly the isosceles triangle we met before. So the length of delta v equals 2v times the sine of delta theta over 2. For a small angle measured in radians, the sine of delta theta over 2 is approximately delta theta over 2, the small angle approximation. The two halves multiply back to a clean result. The magnitude of delta v is approximately v times the magnitude of delta theta. The magnitude of the radial acceleration is the limit of the magnitude of delta v divided by delta t as the interval shrinks to 0. Substitute. That limit is v times the limit of the magnitude of delta theta over delta t, but the limit of delta theta over delta t is the magnitude of d theta dt, which is the angular speed omega. So the magnitude of a sub r equals v times the magnitude of omega. And the direction, as delta theta shrinks to 0, delta v becomes perpendicular to the velocity and points inward in the minus r hat direction. Constant speed, but a relentless inward pull. That is centripetal acceleration. Step back and collect the toolkit. Uniform circular motion is the case where the tangential force vanishes, so the speed holds constant and the only acceleration is the inward centripetal one. The motion is timed by two numbers, the period 2 pi over omega and the frequency omega over 2 pi, measured in hertz. The strength of the inward acceleration has four equivalent phases, r omega squared, v squared over r, 4 pi squared rf squared, and 4 pi squared r over t squared, plus the geometric form v times the magnitude of omega. You choose the form that fits what the orbit hands you, whether that is the radius, the speed, the angular speed, the period, or the frequency. One inward acceleration, many ways to name it. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.